Good afternoon. This will be called Immune Video 4. It's actually the fifth video that we're watching, but one of them we borrowed from the AP Bio class. And in this video, we're going to focus on graphs and also ways that we're thinking of combating COVID-19, SARS CoV-2, and everything from soap to vaccines to some things that you wouldn't technically consider a vaccine, I guess, but more of a treatment. And so we'll see what what headway we might make with that. I did want to start off by saying we're going to explain this thing called the reproductive ratio, R0, and I totally stole how to explain that from Ninja Nerd lectures. So this next little part that I'm going to show you, I completely stole from this guy. So we've got this thing called the reproductive ratio, R0. And when you get deeper into math, you might come up with them having like a subscript 0 and they call it R0. So for flu, the reproductive ratio, there's quite a range. It's from like 0.9-ish to a little bit over 2 maybe. And so I'm just going to go for the middle and say it's got an R0 of about 1.5. For SARS CoV-2, its R0 is thought to be somewhere around 3. Now, that's as of the last time I looked, and I'm trying to stay fresh on everything. We might find out 2 years from now that this number is different. So this is flu, and this is SARS CoV-2, COVID-19. So what does this number mean? Obviously that R0 is double this one. What does that mean? This is sort of like the spreadability or the infectivity of a virus. So let's say that I've got one dude right here. If I have an R0 value of 1.5, that's on average how many people that original guy will infect. And then how many on average each of them will infect. So that means if I was the first guy with seasonal flu, then I on average spread that to 1.5 other people. So to keep it whole numbers, if you infected 2 people with the flu simultaneously, on average, when you came back later, based off of incubation periods and everything else, like the next generation, 3 people would be sick. Each of them would infect 1.5, So now the next generation has 4.5 sick people. I know that there's no such thing as like half a person, it's just stats. So with COVID-19, it's 3. So that means, on average, if I've got one dude, and this is the analogy that I stole from Ninja Nerd, if I have one dude, he infects on average 3. And then each of them infects 3 people. 1, 2, 3, 4, 5, 6, 7, 8, 9. And so 1 turns into 3, into 9, into 27, into 81, into 243, 729, 2187, 6,561, 19,683, 59,000, 177,000. So after 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 generations, when you have the one original dude, after 11 generations, you're at 177,000. Now, this can change. How can we change this? Don't go to school. Social distancing, 6 feet. Only let 100 people into the store at a time. And we can change that R0. So there's a difference between if I've got 20 people in this small room and somebody sneezes, we're probably going to all eventually pass it around and get it to each other. But if I have 20 people in 20 separate rooms and all the doors are closed and somebody sneezes, the likelihood that everybody gets it is slim, social distancing. So we can change that R0 by doing all these things that we've been doing for the last couple of months. Pretty interesting. The next thing that I wanted to show you were a few graphs, and I'm going to have to make an adjustment so that you can see. So bear with me for just a moment. Go right about, you feel like you're floating in space or anything? Go right about there. Okay, so this is from a website called ourworldindata.org. ourworldindata.org. And this one, what's the total number of confirmed deaths? So what I can do, let me scroll to the correct spot here. What I can do is I can just sort of go back by date and recreate these graphs. So here we are, December 31. That's when China basically came out and said like, hey, this is a problem. Sort of they officially said, we're starting to notice this particular pattern. Hey, world, you should know about it. And so that's why we call it COVID-19, because by one day, we named this based off of 2019. If they had come out in January, then we would have called it SARS or COVID-20. So here we can see how many total confirmed deaths are there, and we're down at 0 or so close to 0 we can't see a difference. And then you might remember from our ecology unit, exponential growth. Boom, that is accelerating quickly. And today is April 23rd, and that's April 23rd. You can add a particular country if you want. So of course we're interested in the United States. Close that out, and then you can watch the exact same thing for the United States. So here we go. The world infection starts to go up, and then US starts to go up. Okay, next set of pictures I wanted to show you. Total confirmed deaths. How rapidly have they increased compared to other countries? So this is how often deaths double. So if deaths double every day, then you're going to be on this lane. If it's every 2 days, 3 days, 5 days, 10 days, so it's going to kind of go down like this. Let's get it just right here. So we go all the way back. There's China. So they're following the deaths double every day, deaths double every 2 days, so they're somewhere in between. Now they're slowing down to deaths doubling every 2 days. Now every 3 days. We're at January 21st. I'm sorry, no, we're not. I'm not sure what day we're at. We started at January 21st. And now it's starting to level off. Oh, there we are, March 6th. And then here comes everybody else. By the way, this one spiking up right here is the United States. There's the US. There was Italy. They were ahead of this. So there we go. China is flattened out. And the best you can do on this graph is flat. You can't go negative, right? If you have 0 deaths, how many deaths have you had in the last 5 days? 0, then you'll be flat. So this graph can't go down. Just kind of cool to see how that works. It's horrible because of what we're looking at, but it's cool how you can see and visualize what's going on. It helps to kind of educate people, I think. Next up, daily confirmed COVID-19 deaths. So I've got the world and the United States. So this is how many are being confirmed each day, not total deaths. So that's why it can go down. Maybe today 100 people die. And so the graph is looking like this. And then tomorrow 90 more people die. Doesn't mean that like 10 people rose from the grave. It just means like today 100 people died, tomorrow 90, and so forth. So you can see the spikes as we go. This was a bad day in the United States. That was April 16th, and in the US, 4,928 people died. By the way, in the world on that day, 10,300 people died. So we had almost half of the deaths of the entire world. And then daily confirmed deaths. Are we bending the curve? So there goes China. Their number can go down because daily confirmed deaths, if you eventually get down to like 0, like if nobody died today or yesterday or tomorrow or a week from now, then like you're eventually at 0. So here's China. They peak at 100, a little bit over 100 daily deaths. Then they go down. You'll notice this is on a logarithmic scale, 10, 100, 1,000. So what we're looking for is a downward trend. So the United States is up there where it looks like we're flattening out. Some people are already going down. So it'll be interesting to see what this graph looks like in the future. You'll notice that China right here all of a sudden hops up. There was one day, maybe a week ago or whenever it was, where China said, oh yeah, by the way, I know that we said 0, 0, 0, 0 day after day, but today we're going to go ahead and tack on, and it was like 1,800 deaths or something like that. So pretty interesting. They've got all kinds of graphs that you can look at. I just thought that was cool to show you guys. It's a really interesting way to interact with graphs. It's called ourworldindata.org. Okay, so now let's zoom back out and let's see what we can do about fixing this situation or treating this situation. I don't know that we fix it. Okay, so first off, what can I do? Well, soap. I've heard multiple times that if I wash my hands with soap and water for 20 seconds or more, then that's great. Well, how does soap work anyway? Whether we're talking about a virus or E. coli, you know, before all this happened the last few months, I still knew that I was supposed to wash my hands before I ate my dinner, a hamburger or something, and stuck my hands, basically my hands touching food that goes into my mouth. Well, here's how it works. It turns out that soap, I'm going to draw soap and it's going to look like sperm at first, but it's not. So don't go around and say, Mr. Cotton said that soap is sperm. So with soap, it's got a hydrophilic head, kind of like a phospholipid. You know how phospholipids are like this? You have the hydrophilic head, a phosphate head that's charged. Then we have the lipid tails. Soap actually comes from fat. You somehow render animal fat or whatever the words would be, and you end up getting soap. So it turns out they've got a lipidy, fatty, nonpolar tail, and then they have a polar head. And so what happens is, let's say that you just got some fatty blobs of like bacon grease in a pan and you want to clean it. So you already know that water alone isn't going to get rid of the bacon grease. So what you'll do is, here's a glob of grease, and there you go. So there's a glob of grease, and now I have this soap. Well, if this is happening in water, like in my sink, let's say there's a beaker of water, the lipids don't dissolve in water very well. So the lipids don't dissolve in the water whenever I try to clean my pan. So what I can do is I can put soap in there, and soap again has a polar head and a non-polar tail. So the polar heads are happy to be in the water, and then they stick their tails in the fat. Okay, well now, if I use a wash rag or I just kind of agitate this, then eventually those pieces of soap leave because they're still attracted to the water. So as this soap bubble leaves, or as this little bitty soap molecule leaves, he'll take a piece of that fat with it. So eventually that guy leaves, and that guy, and that guy, and as they do, here he goes, and he's taken a glob of fat with him. This guy leaves, and he's taken a glob of fat with him, and same with this guy. And so as you can see, over time, I'm basically dismantling this glob of fat. So that's how we clean bacon grease out of a pan. You're like, all right, what does that have to do with bacteria, or in this case, a virus? Well, whenever I look at SARS CoV-2, that outer membrane right there, this part is protein, the green, but that outer purple part right there is phospholipid bilayer. Phospholipid bilayer. So if I add soap to the mix, then now soap can destroy the lipid part of that lipid bilayer. So I'm essentially tearing this apart. Same thing with E. coli, same thing with whatever else. Whenever you're washing your hands before you eat dinner or after you work outside or whatever, and that's supposed to kind of take care of the bacteria or viruses, that's how we're doing it. We're destroying the cell membranes. Now you might ask, well, my membranes are made out of phospholipid bilayer. Don't I destroy my own? You would, but your skin is already dead. The outer layers that you see, all of this is dead. So they're just cells full of this waterproofing protein called keratin, not carotene, beta carotene, the orange stuff in carrots, but keratin with a K, and that waterproofs your skin, but it's just a bunch of dead cells held together with keratin and waterproofed. So you can't kill your skin cells because they're already dead. Kind of like you can't kill a rock because it's not alive. Okay, so that's how soap works. That's why you're supposed to wash your hands. Make sure, by the way, that you wash the parts that are touching things. If you're grabbing things with your fingertips, a lot of people wash their hands like this, but make sure you get your fingertips too. Okay, next up, Pitco-Vac. So the Pitco vaccine is from Pittsburgh, is where the pit comes from. And it was I was trying to find what university. So it was a university in Pittsburgh, and this is just a traditional vaccine. So usually what we do with vaccines is this. You might remember this right here is SARS CoV-2, and it's got these red spike proteins. I guess I could label this. And it's got these spike proteins. Remember, those spike proteins fit ACE2, angiotensin converting enzyme 2. You don't have to know the name, just ACE2. And then with the help of this other protein, TMPRSS2, you don't have to know that, it pulls itself inside. So SARS-CoV-2 grabs onto any cells with ACE2, and that's how it latches on. And then with the help of TMPRSS2, it will then pull itself inside, start copying its RNA, and then this cell now becomes a virus factory. It'll start making its own spike proteins and making the RNA, and it'll start like manufacturing the virus. Okay, well, whenever that happens, what we can do as far as this vaccine is we can just go in and make like this particular spike protein. So we can just manufacture it. So here you go. I've got a bunch of this spike protein floating around. Now, the way that that'll work is this. My body has B cells. We didn't talk about B cells a whole lot until the end of the previous immune video, but B cells have receptors on them that can latch on to spike proteins. But these receptors are very, very specific. So out of all the B cells in my body, I might just have a handful that can actually recognize the spike protein on SARS-CoV-2. When it does, that B cell responds by making memory cells, and then it just starts manufacturing tons of those receptors called antibodies. Those antibodies can then come back here and neutralize this SARS-CoV-2. So it'll stick on those spike proteins. Well, if that spike protein has an antibody on it, it can't latch onto ACE2 anymore. So now this guy has trouble invading cells. In the meantime, that antibody is also a yard sign, so to speak, that says, kill me. So then we destroy it. So as far as the PIT-CO vaccine, then the reason that it's working, the PIT coronavirus vaccine is where the CO comes from, is the reason that it works is we just sort of like dump a whole bunch of these spike proteins in there. We're not infecting you with SARS-CoV-2, just the spike proteins. Well, your B cells will happen to bump into some of them eventually. B cells usually get their work done, and antibodies that usually end up showing up. It depends on the disease, but usually it's like 2, maybe 3 weeks. The flu virus, for example, you might have heard, if I get a flu vaccine, then I will become immune, about 3 weeks later. It's when I'm sort of immune to the flu, if we got the mix right. So here's the spike. That's going to hit the B cell. So even though I'm not infected with SARS-CoV-2 at all, I'm just making antibodies for those spike proteins. So now I'm going to have tons and tons of these antibodies floating around. So now let's say 5 weeks later, the real SARS-CoV-2 comes in. I've already got tons of these antibodies to cover it up. So this vaccine works the same way that most other vaccines work. Usually we either take the actual virus, flu or whatever, and we either destroy it and then inject that into you so that your body can start making antibodies for it, or we'll just basically go in and genetically pull out a part and start manufacturing those proteins, inject you with those proteins, and then you still make antibodies for it. It's almost like if we want you to recognize the bad guy, we could kill a bunch of bad guys and show them to you, or we could just take off the bad guy's clothes and say, these are the clothes he'll be wearing. He'll be wearing a shirt like this. This is what his uniform looks like. So that's how the PIT-CO vaccine works. Remdesivir, this one you've heard about in the news the most out of all these, other than soap, obviously. Remdesivir was originally going to help us treat the Ebola outbreak from, I think that was 2014-ish. And so they were working on that, and then the outbreak kind of got under control. Ebola is mainly in poorer countries, so if you're the company that's manufacturing vaccines, you're just going to be losing tons of money. So economically, they sort of abandoned it somewhat. And apparently it wasn't great at helping with Ebola anyway. It was maybe okay, but it wasn't like awesome. So the way that remdesivir works is this. It blocks this guy. So if SARS-CoV-2 enters your cells, it will now inject its RNA inside. Not inject, the whole thing goes in, but like its RNA is now inside. So it's got one copy of RNA. Well then, it will also have a RNA-dependent RNA polymerase. Remember, RNA polymerases make polymers of RNA, hence the name. So this guy basically takes that original piece of RNA and starts making copies. So if I'm SARS CoV-2, I put a virus inside of a cell, and then this RNA-dependent RNA polymerase will just start making copies. So make a copy of that RNA, another. And then of course, these pieces of RNA, plus all the proteins, are now the parts that we use to we now have all the parts for our virus factory. Now this cell can start mass manufacturing it. If this cell is going to manufacture 1,000 viruses, then I need to copy this, and I need 1,000 copies. And I need thousands of copies of spike proteins, and the orange protein, and the blue protein. I need all the pieces so I can start building the viruses. Okay, well the way that remdesivir works is it fools this RNA polymerase. So this is why I have the bricks here. So think of it like this. Pretend that you are RNA polymerase. So what you'll do is you'll look at this. Here's your original strain of RNA. Maybe this is A, this is a nucleotide with A, here's one with U, here's one with G, and here's one with C. So you're like, all right, A, U, G, C. So you look around, there's some RNAs floating around, and inside of your cells, because your cells use RNA also. So you grab one of these and you're like, all right, I need to make a copy. I've got, whatever I said this one was, an A, I need an A. Okay, I need a U, there's a U. All right, I need a G, there's a G. I need a C, there's a C. So I'm gonna make an identical copy and it'll work like that. However, remdesivir is special because remdesivir looks like this. Almost the same, but not quite. So now, here's how this works. I've got my original template strain of RNA. Then, I am the RNA-dependent RNA polymerase. So, I match this up. There you go. There's a match. Cool. There you go. There's a match. Cool. I'm not good enough to recognize that this is not a perfect match. I don't realize that chemically at the top it's slightly different. There you go. So now, when I go and put this guy on there, he doesn't bond very well. In fact, in HIV, there's a drug called AZT. It works exactly like this. And now when I try to bond the next guy, he doesn't stick. So if I grab another one, he doesn't stick. If I grab another one, he doesn't stick. And I can do this all day. So now, here's my original. Can I make a copy? No. So does this become a virus factory? No, because I fooled everything. Now with remdesivir, we think that it's not exactly like that. We think that it is slightly tweaked, but we think that we keep adding bases afterwards and the shape just kind of changes. So I kind of compare it to this. Remdesivir, to be a little bit more specific, is a little bit like this. I have a nucleotide, I add a nucleotide. And as long as everything fits perfectly, a nucleotide. Here's another building block. Get it? Bricks are actually building blocks. And so as I go, I could maybe stack this 50 bricks high if I'm perfect, if everything has the perfect shape, and it'd be stable. But what we do is we put in remdesivir, and remdesivir has a different shape. So it's not quite as thick, and it's not quite as far out like that. So I put it in there, and for a little while it's good enough to stack more bricks. But if I now stack another brick and another and maybe another remdesivir, another brick, another, and another remdesivir, this will become less stable. And so it sort of falls apart, we think. Or the enzyme that's actually hanging on there, we think that maybe the enzyme, because of the shapes, it can't hold on. I can hold on to this, I can hold on to this, I can hold on to this. This one I can't because it's a different shape. That's how we think it works. So remdesivir screws around with the RNA polymerase, and we kind of sneak in a chemical, remdesivir, that's sort of like a faker, which is pretty clever if you think about it. I think that's brilliant. Okay, we've got two more. PIV5. PIV5, if you got like a dog, and you ever board your dog, maybe you go out of town, and so you go to like a vet and you board your dog in a kennel, or maybe like one of those dog places like Dogs Unleashed or Bark and Lounge. You might have heard of kennel cough. Before they'll let your dog even go there for a play day or stay overnight, you have to have certain vaccines up to date. And one of them is for parainfluenza. PI, parainfluenza virus type 5, I guess. So parainfluenza in dogs causes kennel cough. In humans, it's supposed to be relatively harmless. And so here's parainfluenza. For PIV5, here's what they do. They actually take the gene, the piece of RNA that codes for spike protein, and they put that into parainfluenza virus. Then they're going to infect us with parainfluenza virus. So we're going to take this piece of SARS RNA, not the whole thing, so it won't hurt us in that sense, like it's not a complete virus. So they're going to put that in there. They're going to infect me with it. Now, this doesn't make me sick. Maybe it can infect my cells a little bit, but it doesn't make me like, I don't have symptoms of being sick, apparently. And now, every time this virus replicates, it's going to basically make some spike proteins. So this is going to invade your cells, and then your cells will start making some spike proteins. Well, once your cells start making spike proteins, then now this whole response can happen, and we can make antibodies for it. Now, I obviously find some problems with this. If you invade with parainfluenza, I'm assuming it would invade my lung cells. So if you start invading my lung cells and they're now covered with spike proteins, they're either covered with it or they're just manufacturing them inside. Remember, cytotoxic T cells can, when they recognize that one of your cells has something bad inside, their response is to kill it. So I would think that that would end up killing our cells, but apparently that's not the case. Or apparently if we give you the right amount, then, you kill a few of your cells, but you gain immunity or something. I don't know. So that one's a little bit weird. Now here's the most clever one, HRS ACE2. And HRS ACE2 stands for Human Recombinant Soluble ACE2. So Human Recombinant Soluble ACE2. This one's brilliant. Here's what we do. We actually just take that ACE2 protein and we make a soluble version of it. That means we could put it in like a liquid. And so maybe we could inject it, or maybe we could, like a nasal thing. And we just start dumping all these ACE2s loose in your body. So now what that means is, let's say I get invaded with the SARS CoV-2. Well, he doesn't know what he's binding to. It's just that that spike happens to fit ACE2. So if he fits ACE2 on a cell, he can pull himself inside, and that's bad. But what if we just have a whole bunch of ACE2s floating around? Now, all of his spike proteins, instead of being available to infect cells, they're just stuck to ACE2s. So imagine that I have to pretend that I'm SARS CoV-2. And this is these are my spike proteins, and they basically function like a key. And so what I do is I find any cell with the right lock, and I go in. Cool. Now, kind of like if I have a door. I wasn't expecting that for you. So my key fits that lock, I can unlock it and enter. Okay, but now what we do instead is we just have a whole bunch of locks, loose locks, not in a door, but just loose locks floating around. So now here's my key, and here's an ACE2 just free floating around. I'm covered. And here's my other one. Pretend that I just have two spike proteins because I only have two hands. Now this one's covered. Now, let me try to get into that lock. I can't, because I've already got a lock on here. So this guy right here, once he has an ACE2 already, now if he did bump into a real cell, he can't actually invade it. And in tests, they were able to reduce viral load by 1,000 to 5,000 times. So that would mean if normally releasing virus in here in a normal environment, you would infect 1,000 cells. When we were doing this treatment, you would instead infect successfully 1 cell. Because your response might be, well, couldn't this virus still occasionally get lucky and invade an actual healthy cell? Sure. But then it's not as bad. My immune system can handle that. When I'm being attacked and thousands of my guys are being attacked every second, that might be more than I can handle. But if instead of a guy's attacked thousands of times, I have thousands of guys attacked every second, if instead it's 1 per second, maybe I can handle that, right? Here comes a bad guy charging at our door. Easy. Here comes one bad guy charging at our door. Now, if there's 2,000 charging at the same time and I have one gun, I'm screwed. But if I can reduce it down to a small enough number, maybe I'll be okay. So HRS ACE2, to me, is a really clever one. Maybe they've done that before, but I've never heard of that. All right, that should be it for our immune unit. And next up in PreAP Bio, we'll be looking at the nervous system, which is sort of like thinking about how we think.